Hello. Today we will learn multiple regression, but in fact we have learned all elements of regression and regression assumptions. So there is nothing difficult in today's lecture. One difference is multiple regression has multiple x variables, while simple regression has one x variable. Therefore, only one new thing about the relationship between x variables will be added. So far, we have worked with models for explaining outcomes when the outcome is quantitative and there is only one quantitative predictor. Now we will turn to multiple regression analysis, where we will be examining the roles of several predictors. Unlike a bivariate regression that looks at the relationship between one independent variable and one dependent variable, if we want to assess all at one time the different associations that the dependent variable has with multiple independent variables, we can see that relationship better with a multiple regression. Okay, so simple regression anyway violates model specification, right? So we have to run multiple regression instead of a simple regression. So why did we even learn simple regression then? Because we want to know the logic of the regression, as an ideal type. So that's why we learned simple regression. It helps us isolate the effects of independent variables by controlling for the other variables. So when we want to see the relationship between one x variable and the dependent variable, controlling for the other variables, this expression is special in the multiple regression, okay? So controlling for the other x variables, what is this expression as a Latin phrase? It is Ceteris paribus. Have you heard of that before? It is commonly told in econometrics, Ceteris paribus. When we want to know the relationship between one and the other, we want to control for all other factors, because that's how we normally compare something with all the same conditions, right? Yeah. We will see that it is possible to examine categorical predictors using regression, but when there are multi-category variables, it is very tedious, and the ANOVA framework is more sensible and easier to use. So you don't need to worry about this last paragraph because we do not have an ANOVA course as a prerequisite. So actually, we just jump into the multiple regression regardless of the X has categorical variables or continuous variables. It is still multiple regression, so we don't need to worry about this last paragraph. If you have more questions about ANOVA, please let me know by email. Actually, this ANOVA framework is totally different from what you've seen in the multiple regression SPSS output. When you run the simple regression or multiple regression, you see the ANOVA table, right? That table is for model summary and the overall model test. that is not actually ANOVA test. But in this specific slide, ANOVA framework means, analysis of variance. So this is something else. It's kind of confusing, right? But I will talk about it once SPSS output is shown. All right. So in multiple regression, we are modeling variation in Y via a model where outcome is Y equals continuous predictors. So continuous X variables plus error. Okay. So left term outcome is Y. So continuous predictors, the Y hat, and then plus error. Error, different name is residual. So Y equals Y hat plus E, error, residual, okay? Or more specifically, Y equals beta 0 plus beta 1x1 plus beta 2x2 plus blah, 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 beta pxp plus error. For case I means observations, so number of sample with outcome Y and predictors X, 1 through XP. So number of predictor is P. The error are normally distributed with mean 0 and variance, as was true in bivariate regression. There are many similarities between bivariate regression and multiple regression. The multiple regression population model. So population model is not estimated model. So population model includes error term, but estimated model does not include error term. Also, for the estimated model, you have to use Y hat instead of Y. Do you remember the question in the midterm exam? Also, I was asking, identify the parameters and components in the model. For the midterm example, nobody put down these interpretations here. Yi is the score for person I on outcome Y. Beta 0 is the intercept, Y-intercept in the population. Beta J is the slope for predictor Xj in the population, where the slope is the predicted change in Y for 1 unit increase in Xj. Okay, so holding all other X constants. So this part is Ceteris paribus. Controlling for all other factors are the same, right? And error, EI, is the residual for person I. Okay. Note that the error I are still assumed to be independent and normally distributed with mean 0 and variance sigma square. So this is the IID assumption. IID means independent, identically, normal distribution, IID distribution, mean 0 and variance, equal variance, sigma square. So do you remember the question? Specify error assumptions. So that is IID assumption. So you need to put down this sentence. Or EI tilde n parenthesis 0 comma sigma squares parenthesis. Do you remember the midterm exam question? Okay. So every interpretation for each parameter and variable is the same as those in simple regression. But for this parameter, x parameter, you have to include this specific explanation. Okay, this is the difference between simple regression and multiple regression. Okay, Ceteris paribus. Estimated model, yeah, again. So this is a line, estimated line, one single line, so you do not have error anymore. That's why we have to have a y hat instead of a y, because y is observed value and y hat is one single line. There are multiple, residuals. But since we do not put residual error here, you have to have hat. Okay, this interpretation is the same as before, and you just include this one. If we write the model in terms of y hat, there is no error term. Okay. Multiple regression. In the previous two slides, a phrase is underlined. This phrase is holding all other axes constant. Yeah. Ceteris paribus. This is how we specify that we are statistically controlling for the influence of axes other than the one whose slope we are interpreting, by including additional axes in the model. Yeah, so you can add more predictors in the model as long as the model can explain the variance of y better than before, right? It is as if we were equating the cases whose scores we are analyzing on the added axis. Suppose we are examining the role of principal leadership as a predictor of teacher happiness. Yeah, so think about it. If you have a job and, if your boss is disturbing you, then your happiness level will be lower, right? By putting another X, say SES, socioeconomic status, into the regression model. So every employee can have a different SES level, even though the employees have the same boss or, the same, working place. The individual, socioeconomic status is different, right? It is as if we equated scores on their SES scores. Then the slope of the original X shows how much principal leadership affects the teacher happiness for schools with the same levels of SES. Yes, you want to compare. You want to know the relationship between principal leadership and the teacher happiness. At that time, in order to compare each person's the relationship between principal leadership and teacher happiness, you have to hold the same level of SES. Everybody has to have the same SES. And then, based on that same condition, you want to see the effect of the principal leadership on the teacher happiness outcome, right? Otherwise, you cannot know, this different level of teacher happiness is from principal leadership or from SES, you don't know, right? So you have to control one covariate, I mean here SES. All right. So now we bring a concept of control variable. Yeah, do you remember the question control variable in the first research proposal? You know, I asked about your control variable in your research proposal. What is a control variable? Control variable is a predictor that affects the outcome variable, dependent variable, but the researcher is not interested in. Okay, so theoretically speaking, control variable is still backed up by the theory. You know, when you set up your model, when you try to find out your control variable, you still need to go through the literature review, and you have to find out the theories, you know, supporting the X control variables on the Y outcome. So then you can set it up in your model. But that is not your main interest. You have other interest, which is called independent variable, right? So statistically, there is no difference between control variable and independent variable. However, conceptually, you are interested in your independent variable. That's why you call it independent variable. And even though control variables are still influential on the Y outcome variable theoretically, but you are not interested. You are not interested in, okay? Statistically, there's no difference between control variable and independent variable. Anyway, let's read example. Principal leadership is associated with teacher happiness. Yeah, it sounds like research hypothesis, right? So I hope you put some kind of direction in this neutral statement if you want to make a good research hypothesis. For example, good principal leadership is positively associated with teacher happiness, something like that. Right now, when you see this example one, you do not know principal leadership affect the teacher happiness positively or negatively. Maybe the principal leadership can, you know, if principal is too good and the teachers are not appreciated or like happy about it, I don't know. But anyway, whenever you write your statement, please be clear and be specific. Currently, this example one does not have any direction, so it's not that good. Anyway, by controlling for socioeconomic status, we are seeking to understand teacher happiness predicted by principal leadership with the same level of SES. Okay. All right. So the role of control variable. You have reasonable X variables in your model to explain the variance of Y. And you have an independent variable that you are interested in. And also you have multiple control variables. Whenever you explain the relationship between your independent variable and dependent variable, you have to include controlling for all other factors are the same. Yeah, that is something that you remember, you need to remember, okay? Multiple regression interpretation. Okay, so here I put same definition, same thing. This is just like you already learned this interpretation in simple regression. So how do we interpret y-I hat? This is the same as that of simple regression, same definition. X1 through Xn are the independent variable. Yes, the same definition. B0, this is a parameter estimate. Actually, parameter is unknown value from population, right? So it is noted as beta 0 parameter. But here, B0, alphabetical letter, B0 means estimate, parameter estimate. So estimate B0, and the B1, this is the slope coefficient, slope. So B1, B2, B3 in front of X, we call it slope coefficient, regression coefficient, okay? Oh yeah, regression coefficient, yeah, or slope coefficient or regression coefficient. B0 is y-intercept. Difference between bivariate regression, so simple regression, and multiple regression. This is the part of the difference. Holding all other x constant. Constant means the same value, equal value, fixed value, okay? So holding all other x's the same. When we have x's that are quite independent of each other, then adding on x may not change the slope of the original x at all. However, to the extent the x's overlap are related to each other, we may see either bigger or smaller slopes for the original x when a new x is added. In either case, we hope that the added x's explain more variation in y than just one x alone. If they do, it'll reduce the size of residual and thus reduce MSE. What is MSE? Mean square error. Do you remember that? So mean square error. Do you remember mean square error? Sigma y minus y hat square. Okay, sigma, this sigma is not the small sigma, right? So large sigma means the sum sigma y minus y square, parenthesis, right? Y minus y hat parenthesis square, and then sigma. Okay, mean square error. Mean square error. So y minus y hat is what? Error. Y minus y hat is error, and then you don't want to sum them up just as it is because it becomes 0. So what we are doing is once you y minus y hat and then square before sum them up. The square and then sum. Okay. So if you cannot understand this, please go back to the previous video. Okay. Regression. Okay. And therefore, give us more powerful test of the slopes in our model. Yeah. So once you have more x variable, reasonable x variables, you have a more powerful model. Also, adding x's should increase R square, which is one of our indices of model quality. Yeah, model quality, R square. So what is the R square? This is a variance, proportion of variance in Y. Why do you use variance instead of correlation? So go back to the midterm exam, R square question. Okay. Multiple regression assumption. So we already covered this assumption before. This is model specification. Okay. 2 elements for model specification. We have to memorize this, okay? Number 1, all the important x's should be included in the model. No irrelevant x's in the model, okay? So they are 2 different elements. And if one thing is missing, your model is misspecified, okay? So if you have only one x variable, it's model misspecification. So you have to have multiple x variables, okay? Why do I keep saying this? Is because even though you learn these conceptual things, if you do not apply this knowledge to your research model, later you are conducting your own regression analysis for your final project, right? And sometimes students include only 1 or 2 x variables, which is not acceptable because it's definitely violating our model specification assumption, okay? Model specification. When we say we have a properly specified model, we are saying that we have the right or correct model. All the variables in the model have a linear relationship to Y in the population. Having a properly specified model is important because it has implication for our estimates. In particular, our slope estimates will be statistically unbiased if the model is properly specified. This means what? If you include irrelevant x variable, then let's say one x variable is a suppressor over the other, then between 2 x variables there is a highly collinearity issue happens, and also that makes your standard error inflated, and then all estimates is fluctuated, and then the analysis is not valid at all. So model specification is an important regression assumption. That's why we have to read literature fully, and you have to find out really good and important x variables from the theories for your variance of Y. Okay. Statistics does not say anything without any theory. Yeah. So we have to know the topic really well. Yeah. If not, we have to read, or we have to ask the expert. We have to read the literature or ask about it to experts in the field. This means that the long-run average of the values of the repeated sample slope estimates will equal the correct values of the population slopes, the betas. So population slopes beta, sample slope is B, B1, B2, B3, B4, or whatever. One new issue is that multiple regression models assume that the predictors are independent. Yeah, but in reality, they are not independent. What we can do is we avoid highly correlated axes in the same matter. We just want to avoid that situation because, you know, here, yes, multicollinearity. This messing up your standard error. Why do I keep saying about standard error? Standard error is affecting your t-test value. What is the formula of a t-test? We got this before. Do you still remember that? Okay, so I'm not sure you might not know that. So let me just tell you. T equals B slope divided by SB, SC. SC means B is subscript. S standard error. So what is standard error? Standard deviation divided by root n. So do you still remember this formula? Anyway, t-test value, t-statistic, that formula is B divided by standard error of slope, B. So if you have SE, standard error fluctuated, then your T is messed up. So if your T is overestimated or your T is underestimated because of the fluctuation of standard error, then your analysis is messed up. Your p-value is messed up. So what should we do? We want to avoid the situations that SE, standard error, is fluctuated. When SE is fluctuated, multicollinearity happens. Also, when you do not have enough sample size, because SE is equal to SD divided by root n. So if you do not have enough root n, if you do not have enough sample size n, what happens? Your standard error will be your sample size is small, then your standard error become large. Error become large. You do not want to have a large error, right? Anyway, let's read one by one. One new issue is that multiple regression models assume that the predictors are independent of each other, but sometimes they are not. In the ANOVA case, where the predictors are categorical, yes. We can be sure predictors are independent, not confounded, by making sure the group size are equal. Yeah, don't worry about this because we haven't learned ANOVA. ANOVA is a separate class and don't worry about it. Anyway, this is most strictly controlled in experimental design where subjects are often randomly assigned to groups in equal numbers. However, we do not typically assign people to have particular values of axes in regression analysis. So we will need a method for assessing whether our axes are interrelated or collinear. The problem of having interrelated axes is called multicollinearity. So just multicollinearity can be thought as like correlation among axes. Okay. We want to have a high correlation between X and Y, but we do not want to have a high correlation between X and the other X. Okay, it is a high multicollinearity. Okay, and again, don't worry about this part. This is something about ANOVA. Well, ANOVA is a type of regression, but still it is more likely to be controlled experimental design. So don't worry about this part. Multiple regression, many of the analysis for multiple regression have tests and procedures similar to those we have learned already. For example, we will see MSE, mean scale error, and SEE, standard error of estimate. SEE, how can you calculate this one? So once you put root here, then you will have this value, okay? Root MSE equals SEE, okay? Well, we covered this before, actually. So go back to the video if you want to know more about this. We'll use F-test for gauging significance of a whole model. Yes, overall model or omnibus model. We use F-test, right? And the value R square is interpreted as a model quality, but we are not sure if that is statistically significant. So we have to look at F-test and the p-value for the whole model, okay? And we have to assess whether assumptions about our residuals are appropriate using plots of the residuals. Yes, we did it in the midterm exam. We will use the variance explained measure R square. Yes, we did, to assess whether the set of X, so the model, set of X means model. The model we have chosen is helping us to understand variation in the Y outcome. We will also have tests of the individual predictors that will be t-tests. What is new is that we will need to learn to assess whether multicollinearity is a problem for our model. Yeah, so we have to check how do we do that. Just simply run the correlation matrix, okay? All right, here, multiple regression. So this is population model, okay? So beta 1 through beta p is the slope regression coefficients. Beta 0 is y-intercept.